outline for next couple of days. So we are going to learn magnets and electromagnets. So we're going to discover about magnetism, learn about like what is magnetism mean and what are magnets. Then we're going to define the magnetic fields and the magnetic forces, let's say, and see like what produces a magnetic field. Then the magnetic forces on a particle and how those particles are moving. And then we'll learn about the Faraday's law and also applications of magnets or the electromagnets in our daily life. From your view, am I blocking my words over here in the PowerPoint slide with the screen, like my picture or your pictures in there? I'm not sure where I'm keeping my screen. Okay, so if you can see the PowerPoint slide, let me know. So I will try rearranging the setting here, so you should be able to see it.
You can also click on it to move.
Yeah, now I'm moving the picture. So what do you see? Like, is it moving? I mean, my face. I'm moving around. So do you see that? No? Okay.
No.
All right, so I'll keep continue. So if something blocking your view here from my side, let me know. So I'll try changing it. Okay, so this is a demonstration that I would do in the class if you're there. So you can easily make a compass using a metal piece, and you can take a metal piece and rub it on a magnet and make it magnetize. So in any magnet, there are two poles. So remember, like in electricity, we learn about positive charges and the negative charges, where we can separate the positive charges and the negative charges. Like when you're sending a current, we are moving electrons, right? So we can move electrons and we can separate those electrons by different way of charging, like rubbing each other, two objects, you can charge the both objects, right? So by we learn about static electricity. In that case, we move the charges by touching and also without even touching, like conduction and induction. So likewise, in magnets, we have two poles. In electricity, we had two charges. Here, there are two poles. We call those as north pole and a south pole. Specifically, the north pole is a north pole in a magnet is a south-seeking pole, and a south pole in a magnet is a north-seeking pole. Now, on Earth, you know, like we say northern hemisphere or the southern hemisphere, and we're looking at the north side when we are using a compass. So if you have your phone app with a compass, I think every phone comes with a compass. So if you look at for your extra icon, so this is a Apple phone. I don't know what phone you have, but if you have any smartphone, you should be able to find it. So if you go to this extra links, by the calculator and all, we can find a compass, right? In a compass, you see like this one. So we don't need a physical compass these days. We can use our phone app for the compasses, right? So in this one, we see there's a North Pole indicator, and it's always pointing towards Earth geographical north, right? Now we learn here, the North Pole is a south-seeking pole. So here's a compass, and the compass's North Pole is pointing to the geographical North Pole of Earth. Now here's the theory, North Pole of a magnet is south-seeking pole. There's a little mismatch in there, right? So Earth geographical North Pole, is it a magnetic North Pole or a magnetic South Pole?
Magnetic
So
south?
Yeah, it should be, right? Because compass is a little magnet here. So this is a magnet, and the magnetic North Pole is seeking a south magnetic pole. So Earth geographical North Pole is a magnetic South Pole. Now, if you think about Earth, around the earth, there's a big magnetic field lines going around, and basically there's a big magnet embedded inside the earth like this one. So the south magnetic pole is in the geographical north pole. Now here, if you keep a compass, basically compass is a little magnet. So the magnet's north pole is seeking the geographical north pole here. But basically this is the magnetic south pole of earth. Now, don't misunderstand it with the rotational axis, because earth rotational axis and the magnetic axis is tilted by 23.5. So there's a little misalignment with the rotational axis and the magnetic axis. So the north, or the north seeking pole of a compass, points towards the earth north pole. So the magnetic field produced by the earth can be pictured by imagining a larger bar magnet inside the earth, like in this picture. So there's a big magnet inside the earth embedded in there. That's what we can create our model depending on. Then the, like unlike poles attract, like in the electricity, likely charges repel, unlike charges attract. Likewise here, in the magnets, unlike poles attract. So it's very similar to electrical charges. Then the south pole of the earth magnet must point in a northerly direction. So that's our argument about the earth geographical north pole. So basically, geographical north pole of earth is a magnetic south pole. The axis of the earth magnet field is not aligned exactly with the earth axis of rotation. They are 23.5 offset. But the center, like it's the rotational axis and the magnetic axis are cross at the center of the earth. So they are not misaligning. They're crossing at the center of the earth, but they're off by, tilted by 23.5. Okay, so here in this picture, the blue color line represent the, let's say the magnetic axis. Then the red color dash line represent the rotational axis. So this angle over here is a little bit offset by about 23.5. So it's very similar to the earth tilt. All right, now, have you ever noticed northern lights or the southern lights? Or we call these as aurora boreas. Do we have anyone who saw these? I always wanted to see this, but didn't have a chance to. Do we have anyone who saw the northern lights? No? We are almost there. So if we travel a little bit higher, like upper Michigan, we should be able to see the northern lights. Also Washington, state Washington, and that area, we should be able to see these northern lights. So this happens due to the earth magnetic field and the sun's solar charge flares. So the earth does have a magnetosphere. So there's a protection against the solar flares. So this is not ultraviolet light, okay? I'm not talking about UV, I'm talking about a different thing. It's a charge particles that's sent by the sun. So that's a different thing than UV light. So don't get confused. UV light is a different thing, and the earth does have an ozone layer to protect us from the those UV lights. This is different. This is a magnetic field around the earth. Like in this picture, we have a magnetic field lines around the earth like this one, like in this picture. So these are called the magnetosphere around the earth. And these magnetic field lines protect us receiving those extra or the unwanted charged particles that's coming out from the sun. So as you see here, the magnetic field lines are around the earth, like nicely arranged like this way. But if you look at over here at the top and the bottom, like very north and the all the way down at the south pole, there's a little opening over here. so the charged particles can enter into our Earth atmosphere. So when the charged particles enter into the Earth atmosphere, it starts scattering. So when it scatters, it creates these nice colors into the air. So that's why we see these colors. So if we didn't have this magnetic sphere around us, then our sky will be more colorful than just having blue in the daytime. So we call these magnetic field lines as the Van Allen belt. So we have Van Allen belts around the Earth, protecting us receiving unwanted charged particles that's coming from the sun. So here, if we analyze the layers in the atmosphere, so we have by the ground about 10 kilometers high, we have the troposphere. Then up to about 50 kilometers, we have a stratosphere. Then from 50 to about 85 kilometers, we have mesosphere. Then after that, 90 to about 500, it is the thermosphere. Then after that, it's exosphere. So this red color line represents the temperature. So when you go high in the sky, we feel like it's getting colder. Yes, it is true up to 10 kilometers, but after that it's increasing its temperature. Then again, it decreases the temperature, and after that it's again increasing the temperature. So the temperature is varying in the altitudes. Like when you are traveling up in the sky, the temperatures increases and decreases. So it's not really like here, this is the normal temperature in our atmosphere, but when you go up in the sky, it's go to negative 50s Celsius, and it's coming back normal like 0 degrees, and then go low like negative 100 Celsius when we rises up to about 100 kilometers. But after that, it's increasing its temperature. So that's where we have the Earth atmosphere coming in. So Earth atmosphere, when it's starting Earth atmosphere, it gets heats up. So here the temperature is a little bit high. So so we have this atmospheric protection from these magnetic field lines. So the magnetosphere blocks charged particles that come, the ionosphere, a high level layer of Earth atmosphere, stop the radiation from solar flares. So we are not receiving this unnecessary radiation that's coming from due to the solar flares. So every day, charged gas particles within 153 mile deep ionosphere absorb radiation and prevent it from reaching Earth's surface. So but there are places that when we receive the high intense solar flares, we receive it. So I still remember, like in 2016, middle of winter, we received a huge solar flare, and in Chicago, we had summertime in the middle of winter. So that's due to a solar flare that happens, and it heats up, it radiates the environment and make it more warmer. But we didn't see the color lights. It's in the daytime, we can see these colors, but in the nighttime, we should be able to see these color lights that happening due to this entrance of these unnecessary charged particles that's coming from the sun. All right, so now let's learn a little bit more about these magnets. So that's one effect that we are seeing in the natural world. Take me off from the screen sharing. Okay, here we go. Okay, so let's say we have magnets. That's now we know there are two poles in a magnet. That's North Pole and South Pole. So in these pictures, the red color represents the North Pole and the blue color side represents the South Pole. So what happens if we bring two poles close to each other? So we know that so it's North Pole, you're bringing North Pole together, so they repel. And then South Pole together, they repel again. So that means the like poles repel. Very similar to the electricity, where likely charges repel. Now, when we bring a South Pole and a North Pole, they attract. So unlike poles attract. Now, in this picture, I draw these arrow lines to represent the forces. So if something is repelling, that means there are a force that's pushing against each other, right? So the force is acting against each other. So this FB represents the force due to the magnetic field. Why it is B? I don't know. That's how we label the forces due to magnets, right? So FB means the force due to this magnet, so magnetic force, let's say. So basically FB represents the magnetic force. So North Pole together towards, that means they're repelling each other. So there's force that pushing against each other. So this is the direction of force. Now, when you are bringing North Pole and a South Pole, they are likely poles. So there should be some attractive force going on. So here they're attracting to each other, towards each other, right? So unlike poles attract. So that's an analogy to electricity. I think you now understand it, right? All right, then let's see, like if now we have a magnet and I like to break it and I want to separate just the south and just a north pole, like electric charges. So I want to separate single south pole into one side. Can we do that? So in order to do that, we need to break this magnet into pieces, right? So when I break the magnet into pieces, I again create a north pole and a south pole. I keep breaking the magnets, let's say, then there's tiny, tiny magnetic pieces coming up, and still I have a north pole and a south pole. So there's no way that I can create just a single south pole or a single north pole. So we call this as the monopoles. So there are no magnetic monopoles. Monopoles means just a single pole, like a single south pole or a single north pole. So this is a project for you. If you are interested, you may start looking at searching for magnetic monopoles, and the Nobel Prize will be yours. But remember to include my name. All right, so then what happens if we break a spherical shaped magnet? Can we isolate a monopole? No, if it is a Nobel Prize, we still don't know, right? So no, we cannot do that. Even though you are breaking any shaped magnet, it doesn't matter. It will automatically creating its north pole and a south pole, like in this picture. Yeah, so the shape will be spherical, but there will be a magnetic pole and a south pole within the magnet, like this in this picture. All right, so we know that there are permanent magnets. So permanent magnets is the magnetic strength is there, so we cannot break this magnetism in there. So those permanent magnets does have a north pole and a south pole, and it does create magnetic field lines. So here in this picture, you see a magnet in there, and a red side represents the north pole, and the blue side is the south pole in the magnet. And what are these black colored dots? Those are iron powder. So when we spread iron powder around a magnet, you can nicely see this iron powder arranging it in a fashion like this. It's very similar to electric field lines, right? It's curving around the poles. And here it's more stronger. And then when you're going away, the strength is getting reduced. I know it's hard to believe because this is just a picture. So I think I included a video here. Let's see. Let's say I keep a magnet here, and then I spread a lot of little bit small size compasses around it. So you will see that the compass is aligning in this fashion. So basically, the north pole of the compass is seeking a south pole. So they are arranging in this fashion. So if you notice this arrow's direction, this arrow is always directing towards south, right? And over here, it's towards the south pole. So this is the north pole, and that's the south pole of this permanent magnet. How did I find it out? I have to use compasses. So I spread compasses around the magnet, and I see the north pole of the compass is seeking this side. So this side should be south pole. So if that side is south pole, then this side is the magnetic north pole. So basically, the direction of the magnetic field can be defined as the direction of magnetic field where the compass will point. So the compass's north pole is pointing to magnetic south pole. So wherever the direction of magnetic field defined, you can define it as the where the compasses is pointing. So for example, this one, it is a compass with north and south pole in there. And if we draw the magnetic field lines, it will be like that. So starting from north pole, and it's go towards the south pole. It's similar to the electric charges, like where electric field started from positive side and go towards the negative charges. Here, the magnetic field lines start from North Pole and go towards the South Pole. Now, what happens if I bring two magnets close to each other, like in this one? So I have North Pole, and a South Pole, and a South Pole. Now, each magnet will create magnetic field lines like this, right? Then, as they are together, these magnetic field lines cannot cross each other. So it will arrange nicely in this pattern, very similar to the electric field lines. The only thing over here is the direction. It's starting from North Pole and go towards South. Over here, it is north-north, so it is repelling each other. In the middle, it is zero magnetic field. So if you want to send a charged particle through this, I will send it at the center because there's no magnetic field in there. So in the accelerator facilities, when we separate these charges, we are using this idea. So we keep the magnets around the beam line, and we can bend these lines using these magnets. Okay. So the units for the magnetic field is, it's a new unit. It is called Tesla. It's uppercase T. 1 Tesla means 1 Newton amps meters. Newton per amp meter. Okay. So you don't need to remember this one, but remember that the magnetic field unit is Tesla. So that's a name of a scientist, Tesla. So if you have visited Niagara Falls, maybe you have seen a big statue of Tesla, the scientist. So because in Niagara Falls, people are producing the electricity by using the technique that Tesla found. So there are beams that, motors inside the waterfall that's create the energy. So that whole area get powered by the hydraulic energy that produces using the Niagara Fall water flow. Okay. Now I'll use this simulator, giving you a little bit detail about these magnetic poles. Let me open that simulator.
What does that M stand for in that equation you just gave us? Or the Tesla?
Meter.
It's meter, M, meter.
Okay, thank you.
Okay. That's my simulator. Okay, here we go. So I think I should be able to share that. Here you go. All right, so in a real class, I would give you a compass and a magnet, and I'll ask you to draw these lines. So I want to practice you to draw these field lines. Like in the homeworks and exams, I will give you multiple choice questions, so you never get a chance to draw it. But if you like, if you're taking notes, you may do that now. So let's say this is a magnet. So you see clearly that there's a North Pole and a South Pole. So there should be magnetic field lines that's going around this, right? So it should be starting from north to south. So what I'm going to do is I'm going to put some compasses here. Or let's say show field. Okay. No, let's use a compass. So here I kept a compass. So in the compass, the red color arrow is the North Pole of the compass, right? So this one is pointing towards the south. Magnetic South Pole, right? Now, if I move it here, look at how the direction of the arrow changes. So again, this red color point is pointing towards south. If I move it here, it's bounced back, but it's points over here. So the magnetic field line should be going like from here to there, like curving around. Now, if I bring it over here, it points the opposite way, right? So it's because it's seeking this South Pole. So it need to go all the way around, reaching to the South Pole. Now let's say I keep it over here. See the change? It's changing the direction, aligning it towards the South Pole. Here, it points that way, right? Here, it points south of the magnet. Now, if I put whole bunch of magnets, compasses, I mean, if I put whole bunch of compasses around this magnet, this is how it's arranged. So the compass needle, the red color needle points towards the south. See, this is the direction. So if you follow the direction of this red color points, it's represent the field direction. So the magnetic field is start from North Pole and go all the way towards south. Okay. So if you're trying to draw the field lines, you need to connect these lines. So let's say this one. So I will connect it from here, 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 and here. So it's curving around. So you are starting from North Pole and draw a curved line towards south. So the direction is towards south. So always you have to use arrows to represent the direction of anything that has a direction. So we call those as vectors. So I didn't talk about vectors yet because I start from electricity. I should have start from motion. Then we should have learned about vectors, but we will learn about it in the later part of the class. For now, remember that vectors means it does have a direction and a size. So the magnetic fields have a size and a direction. So we call the magnetic fields as a vector. So here, direction is from north to south. Now, let's look at what's happened inside the magnet. So this is around the magnet, right? So what happened inside the magnet? Think about it. So the red side is pointing towards north, right? So inside the magnet, it's flipped. So the compass, if you can embed a compass inside, you will see it's pointing to the north, north, north. All right, so let's see the planet Earth. Here you go. So look at the field lines. So the little compasses are pointing towards the geographical North Pole, right? So when you're using your compass, it's always pointing to the geographical North Pole. But remember, that is the magnetic South Pole. All right. Now, next one here. We call this as bar magnets if the shape is like a bar, like a chocolate bar, right? This is a bar magnet. So here, here's the field lines again. So it's going from north to south and north to south. So we know that already. And then there are some other magnets as well. Now look at this one. It is a battery and a kind of a solenoid, right? It's a coil that can current carry on. So here you see this coil is connected to the battery. So there should be current going through this. That means there are moving electrons, right? So that blue color dots represent the electrons. So there's an electron flow in the coil here. Now I'm curious to see whether there's a magnetic field around it. There's no magnet in here, right? So can we have a magnetic field around here? So in order to check that, we need to use a compass, right? So let's put some more compasses around this. So actually I use just one compass. Look at that. There is a magnetic field here, right? It's changing. So it is not measuring the Earth North Pole, but something else, right? See, because it's changing its direction. Now, if you took your compass and if you walk around your house, you will see it's always pointing to one particular direction. That's the Earth North Pole. But here, it is really not. It's changing its direction. So there's some other magnetic field is affecting onto this compass, right? So let's look at the fields. Look at that. So there's a magnetic field around this coil. Look at it. So the compasses are pointing from here to there, right? So it's going around here. So this change happened due to this flow of current. So let's say I want to switch off this battery. So this is 10 volt, 4 volts, and I want to switch it off. Here you go. I make it 0 volts. So there's no flow of electrons. Electrons are still there, but they're not flowing. So there's no magnetic field lines around it. See, when I move the compass, it's always pointing towards somewhere here. So there's no magnetic field coming from the battery or from the coil, I mean, from the coil due to this flow of electrons. Now here, I'm making a small change, giving a little bit voltage here, changing the battery. Now it's create a field lines here, right? So when electrons are flowing, it's creating a magnetic field. Why is that? That's confusing, isn't it? Okay, I'll take you back to my PowerPoint slide. So there should be a source to create these magnetic fields, right? So in a permanent magnet, we know that a moving permanent magnet, we know that there's a magnetic field around it. Now let's look at this little experiment here. I wish we can do it in the class, but here you have to watch my weird video here. I think you can see it. So here there's a coil, a solenoid. We call this as a solenoid because it's a coil that the current can go through. And here's a compass in the middle. And I want you to watch what happened to this compass when I send a current through the solenoid. So here I'm playing it. You just wanted to watch it, it's not a audio, it's just a video with no audio. So you just watch what happened to the compass inside the solenoid over here. Okay, so here, no current, so the compass is pointing that way. Now I'm going to connect the battery to the solenoid over here. Then let's see what happened to the compass. See, it start moving, right? So when I send a current through the solenoid, I see a deflection in the compass. So when the current flowing through it, there's a magnetic field created inside the solenoid. So only reason that we can imagine is the current, right? So the current means moving electrons. So moving electrons is the cause of creating these magnetic fields. So charged particles creates a magnetic field only when the charge is moving. Now there's a solenoid and there's no current through it. Are there any electrons in there? There should be, right? Because atoms are there. So the electrons are there, but there's no flow of electrons. So we don't see a magnetic field. But when there's a moving charged particles, that means moving electrons, then it's create a magnetic field. Okay, so that's fine with these electromagnets because I send a electricity and create a magnet. So we call this as electromagnets. Now, what about permanent magnets? Then how do permanent magnets get the magnetism there? So in theory, the magnetism is created by moving charges. Then there should be moving charges inside a permanent magnet as well, if this is the theory, right? So where this permanent magnet get these magnetic fields or the magnetism? That's coming from these tiny electrons in the material. So the electrons are really, really vigorous. They're moving around and also they spin up and down. So let's say electron is just standing up here. It's not that huge, but as in this picture, electron is here and it's pointing in this direction and suddenly it spins back. So always electrons in spins up, spin back, spin up, spin down, spin up, spin down. So that's create a change in the magnetic field. So these electrons are orbiting around itself, like Earth rotating around itself, electrons are orbiting around itself. At the same time, it flips up and down, spin up and down. So that's create the magnetic field in there. So inside permanent magnets, there are moving charged particles. Those are electrons. So these electrons can spin up and down and also it rotates around itself, creating these magnetic fields. So magnetic moment of an electron means the electron, we know it is a charged particle that has a negative 1e charge. By now we know what is the charge of an electron. It is 1.6 times 10 to the power minus 19 coulombs. I'm sorry, this PowerPoint slide does not show the correct format here. It's 10 to the power minus 19 coulombs. I think I had a homework question about this, so I believe you know that. So the charge of an electron is 1.6 times 10 to the power minus coulombs, and we call this as a negative E charge. So in an electron, there's it is a charged particle with a negative E charge amount, and it is an elementary charge. So it does have an angular momentum that's come from types of rotation, spin, and orbital motion. So orbital motion is like Earth rotating around itself. likewise electron is around rotating around itself. So that's come from that orbit and the spin up and down. Earth is not spinning up and down, but electrons does. So basically these electrons behave like a tiny bar magnet. So there's a north pole and a south pole to the magnet. So if you are taking upper level quantum mechanics, then we can learn about these spinnings of electrons. Here in this class, I'm not going to talk about the quantum mechanics of this electron spinning up and down. Now, there are materials that are magnetic, and also there are materials that we can make it magnetic, but easily we can remove that magnetism in there. So the here, as you see in magnetic materials, we have these tiny magnetic particles in there that it has a magnetic quality like North Pole and South Pole, and they are loose and randomly distributed. But when we bring a permanent magnet or a magnet closer to it, then these little magnets will arrange itself in this nice orderly fashion, creating one side is North Pole and the other side is South Pole. So here in this magnet, you see this side is South and this side is North, and in the middle, South, North together. So you don't see a separation of the magnets there, but at the edges, this is North and that's South. Now, when you break the magnet in the middle, let's say I'm breaking it from here, then you again have a red side over here. So this side will be North Pole and the other side is South Pole. Let's say I'm going all the way down and make a little piece here. Again, you will see a North Pole here and a South Pole here. So that's why we cannot isolate these monopoles, like just a one South Pole or a one North Pole. We cannot do that because inside the materials, this is the arrangement. So you see like it's arranged nicely. But there are materials that does not have any magnetic properties like this. So you cannot magnetize those. You cannot arrange it. So again, my question again. So how does the magnetic field create in a permanent magnet? So basically that is due to the moving charges. So the permanent magnets and the electromagnets are two types of magnets. They are producing the magnetic fields by quite different way, but they all uses the idea of moving charges. So there are moving charges that create the magnetism in them. So it doesn't matter whether it is a permanent magnet or an electromagnet, it's coming from this movement of electrons. If that's so, we have these current carrying wires around our houses. It should create magnetic field lines around it, right? Because it's taking current in there. So there are charges or the electrons flowing through it. It should create magnetic field around it. That is true. So unless we have these cords like plastic or the rubber cord around the wires, there should be magnetic field coming out from there. By using these insulating materials, we always protect the environment with unnecessary magnetic field lines that arises by those wires. But if we have a bared wire, like open wire, then if we keep a compass around the wire, we should be able to see the compass needle get deflected. So first time Oersted discovered this thing. So when we have a current carrying wire, it's create magnetic field lines around it. So if you have a battery and a wire that's open wire, so you need to remove that plastic cover around the wire. And if you connect that wire to the battery and if you keep your compasses close to it, then you should be able to see that the compass get deflected differently. So these current carrying wires does have a magnetic field around it. So it's due to the movement of these electric fields. Before we go to do some activity on top hat, let's learn a couple of things more. So the B fields. Now, if there are current carrying wires and if it is creating magnetic field lines, then we should be able to demonstrate it, right? So I believe you can see it. I'm not sure, but this PowerPoint slide is available on the canvas and also top hat. So you can play this video in there. So here I have a copper wire going into a paper, and then I coiled it. So this is a coil that's going inside the paper. So it's basically taking current in and it's put the current out from here. Now here these black color dots represent the iron powder. So it's a finely grinded iron. So it's just a like sand. So it's a iron sand here, and this is a current carrying wire. So you see this magnetic powder is just distributed randomly around. So there's no pattern here, but let's see what happened when I start sending current. So this is in the beginning, so there's no change. The magnetic powder is just randomly distributed. Now I'm sending a current. Do you see something? It's changing the pattern of the magnetic field powder, right? See, it's arranging nicely around the current carrying wire. I wish we are in the class and you should be able to see this. It is really thrilled to see like when it's happening in front of our eye, but we can't do it. So let's watch this video. So in the beginning, the magnetic field, iron powder randomly distributed, but when you're sending the current through the wire, you see this the iron powder arrange itself nicely in a pattern. Right? So why is that? So the iron is attractive to magnet. So there's a magnetic field created around this wire. So that's why it's arranged itself. So this is the pattern of the magnetic field lines. Now, when we have a current carrying wire, so look at this picture. This is a wire. So in the picture, you can't see it, but it is connected to a battery. So here, the current is not going through because let's say switch is open. So there's no current going through it. So I equals 0, that the current going through the wire is 0. Now there are a bunch of compasses. They're pointing towards one direction. That's pointing to the Earth geographical North Pole, right? So no current. The compass needles point geographical North Pole of the Earth. Now here, in this picture, we are sending a current in the upward direction. Okay, so current going upward direction. Now you see the compasses are pointing in a circular direction here, right? So we call this as tangent. So this compass needle is tangent to the circle around here. So if you draw a circle, this compass is in the tangential direction. All right, so we can find this direction using our hand. So B field is a vector. Now this is how we can find the direction of the magnetic field of a current carrying wire. So you use your right hand. I don't know whether you can see my my picture on your screen. Hopefully, I think you do. So here you use your right hand and you keep the thumb in the direction of current, like in this picture. So this thumb is in the direction of current, even here. So here, right? And then your four fingers are curving in the direction of magnetic field. See, these four fingers are curving in the direction of magnetic field. I want you to try it. Okay, so you keep the thumb in the direction of current and then the four fingers are curving in the direction of magnetic field. You are using your right hand, not the left hand, right hand. Okay, so we call this as the concentric circles around the wire. So around the wire, there's magnetic field and these circles are concentric. That means the wire is at the center and all these circles take magnetic field. So around the wire to the infinity, we have a magnetic field that created by this wire. We can calculate that using this equation, B equal mu naught I over 2 pi r. I am not going to explain this one right now. It is for tomorrow, Thursday class. So R means the distance from the wire. I is the current and mu naught is the permittivity of the materials. Yeah, for now, just forget about this equation, but it is coming up. I want you to learn about the direction in this activity. So the current is upward direction. So you're using your right hand, thumb along the direction of current, then the four fingers are curving in the direction of magnetic field. Now, if the current going downward direction, what happened? So you point your thumb in the downward direction. So the direction of the magnetic field lines will switch. It's opposite. So it will be going in the other way around. Okay, so I will take the attendance on top hat and let's try a couple of questions there. Okay, so on top hat, when you want to review the problems that we did, you have to go to assign. So there's a link, like the second tab on your top screen of the top hat, there's a assign place. So you go to assignment. So there you can review all these materials in there. Okay, so let's try one question, but before that,
Professor,
the attendance. Yeah,
my top hat has erased your class
erased.
and it won't let me search it up and I don't know what to do. It won't let me refresh
That
either.
the
It
top
did that
hat.
the last class as well.
I didn't erase it, so it should be there. So we have to contact the top hat help. So why don't you email me after the class today? Then I will forward that to the representative. Do we have anyone else have the same problem? No? Okay, I didn't see who speak up. So I have 111 students, so I didn't see who speak. But can you please email me after the class? So I will forward that to the representative, so they will help you.
Yes, ma'am.
All right, so others, can you see the attendance code? Okay, nice. I see that you are replying me. Okay, so I'll keep it minimized and open and let's do the questions. All right, so it's a very straightforward question. So let's look at your answers. Yeah. So with magnets, very similar to electric charges, likely charges repel. So likewise, likely poles repel one another. Yeah, those who answered answer A, likely poles attract one another. No, it's not. North, south attract. That's north and south are not likely poles. Okay, let's try the next question. Okay, so here a magnet on a frictionless mount, that means you are not holding the compass like tightly bounded, like, oh, let's keep the North Pole this way. You are not doing that. You let the compass needle move freely. That's what it means. Okay, let's look at your answers. All right, so we are confused here. Let's see. A magnet on a frictionless mount would have its magnetic north pole point towards the geographical. Magnetic north pole points toward the Earth magnetic south pole, but magnetic south pole is geographical north pole of Earth. Think it again. So magnetic north pole of a compass points towards the Earth magnetic south pole, but Earth magnetic south pole is the Earth geographical north pole. Anyone want to argue with me or comment? Where did I make you confused?
Can you explain it in drawings?
Okay. No, I think I will go to instruction. Okay, so here, this is a bar magnet, right? So this is North Pole and that's South Pole. Now, this compass, what is this red color arrow represents?
North.
That is North, right? So this North Pole, that is magnetic, right? This is a compass is a magnet, and this is a bar magnet, which is a magnet again. So this magnetic North Pole is seeking a magnetic South Pole. That's true, right? You agree or no?
Yeah.
Yes. Now I'm going to bring the Earth. Okay. So, you know, like this is our geographical North Pole and that's our geographical South Pole. Okay. So this is where North America is, right? So North America is in the North Pole. So this is the geographical North Pole. And here, this is Australia. So that's South. So that's the geographical South. Now look at this compass. The compass needle is pointing towards the geographical North Pole. But in our theory, we know that the compass North Pole is seeking a magnetic South Pole. So there should be a magnetic South Pole over here. So the geographical North Pole is magnetic South Pole. Here, geographical South Pole is Earth magnetic North Pole. Okay, let's go back to the question here. Magnetic North Pole of a compass points towards the Earth geographical North Pole. But if I say Earth magnetic, then it is magnetic South Pole. Okay, let's try the next question. I think I have the... Yeah, I will add a couple of questions onto the homework and it will help you. So there will be 2 attempts on the homework, the upcoming one. So you can try, if you got incorrect answers, then you can try it again, but please try to understand it so you won't get confused in the exam. All right, so the magnetic field lines of a bar magnet. What is the direction of this magnetic field lines? Okay, are we all good sending the attendance code? I'm going to stop counting attendance. Do we have anyone who needs more time on the attendance? I think not, so I'll finish counting it. Okay, let's see your answers. Yeah, so it's emerged from the North Pole and go in towards the South Pole. That's the direction of magnetic field lines. Okay, so if you got it incorrect, then you need to go back, look at the PowerPoint slides and see the direction. So the magnetic field lines start from North Pole and go towards the South Pole. So here in this class, the direction or the arrow directions are really matter. It's showing the direction of things, right? So if you look at the magnets and if you look at the field lines, you see like it's starting from North Pole and go towards the South Pole, curving around. Oh no, that's it. Don't answer it because, oh yeah, maybe we can try it, but I know you don't have any idea what is this dots and cross. So I will help you here. Okay, so in the question, it's asking you a cross section of the magnetic field for a current carrying wire is shown. The direction of the current is, so it's asking the direction of current, and in this picture, so please stop answering. Let's discuss this. Then you can answer it, and also there will be a couple of questions on homework. But I'll go over this one again on Thursday. So here, this crosses and dots. What's that represents? So it's represent an arrow, like like in arch race, you're sending arrows. So the arrow back, like if you're looking at an arrow from the back side, you see it's back like a cross, right? And when if an arrow coming towards you, you see the front of the arrow, which is a point, right? So this means it's coming towards you. Hold on. So here, this side, the dots means it comes towards you. And this crosses represent it's going away from you, right? So you're looking at the screen here, the computer screen. So dots means it's coming towards you, and crosses mean it's going in to the screen, right? So it's curving, right? So you think about something coming out from here, from the bottom, and here's a wire, and it's from the bottom of the wire, magnetic fields comes towards you, and then on the top of the wire, it's going in. So it's kind of curving around, right? So it's curving around. So what you have to do is you take your right hand and your 4 fingers, curve it in the direction of the these dots and crosses. So from the bottom of the wire, it comes towards you and then it's curved around, right? So I think my video screen is coming to you as a mirror image. So it's flipped. So I want you to try. So keep a pen in front of your computer and keep it along this wire. This is a wire. The black color line is a wire. So keep the pen along that black color line that represent the wire. And then you take your right hand, 4 fingers on the bottom of the wire. It's curving. It's coming out of the page, right? And then it's curved around the wire. So what direction of current represented by the thumb? So what is the direction that the thumb is pointing to? To the right, to the left. Okay, I'll keep open the question so you can answer that. So this is, I took you to a little bit second step, I guess, for a problem where you can find the direction of a current on a current carrying wire, because by finding the magnetic field direction, you can go to the second step of finding the direction of current. Okay, I think most of you answered. So let's look at your answers. Again, it depends on how you're looking at it. So I want you to keep, look at the screen and from there, think about it, okay? So I think you got the incorrect answer because you are not aligning your directions with the screen.